Hello everyone. Let's start today's lecture where I intend to finish chapter 12, which is the last chapter of our book. So what we're going to see at the second half of chapter 12 is what everybody's been expecting, or I hope everybody's been expecting, which is an introduction to machine learning, more specifically to neural networks, to neural network in machine learning. We're going to see some of the foundations for neural networks. We're going to start with the fundamental idea. Everybody has to start from the perceptron if you want to understand what a neural network is, what a deep learning model is. You have to start from the beginning, which is the perceptron. And although perceptrons are not used in the current neural network implementations, the operations they perform are almost identical to those of artificial neurons. Let's see then what a single perceptron does. A single perceptron is just a computational unit that learns a linear boundary between linearly separable pattern classes. I have to make this more specific, right? It's linearly separable classes. So a perceptron only works with linearly classes, linearly separable classes. So this is the simplest a very simple two-class example where you have one data item that belongs to class C1 and one data item that belongs to class C2. What the perceptron does, it learns this boundary separating classes of objects of the kind C2 from objects of the kind C1. So basically, what the perceptron learns is the function of a line. It's a linear function, right? It's the expression of a line. So it has to learn two things: the coefficient or the slope, and the y-intercept. In neural network terms, in a more general way of expressing this equation is written as W1 x1 plus W2 x2 plus W3 equal to 0. So this one, that's the notation that we use in neural networks. It's nothing more than exactly this. This is the equation of a line, of a straight line. Okay. So, as it's explained here, linear boundary in two-dimensional space is a straight line with equation y equal to ax plus b, where a is the coefficient or the slope of the curve, b is the y-intercept term. But in neural network terms, the y-intercept term is understood as the bias or bias coefficient or bias weight. Yes, unfortunately, they use the same word bias that we used before, but we used before in a statistical term. It's an overloaded. So bias here has no relation to the statistical bias or to the bias in a kernel that we discussed before. So this in neural networks, when we say bias, we are usually talking about the y-intercept term on these equations. For higher dimensions, we need a more general notation. So we use coordinate points as x1, x2, and so forth until xn. And the coefficients of every axis would be w1, w2, and so on. And we usually use a Wn plus 1 as the bias term, as the well, it's not a y-intercept term, that's why they use bias, as the intercept term. So the boundary separating classes in more than 2 dimensions are not called a line, but it's a hyperplane. So this is an equation of a plane that's also expressed, can be expressed by this sum. It's basically a sum of terms, right? It's basically expressed by this sum, and in vectorial form, we can use this as a matrix multiplication here, plus this bias term. In matrix form, this W matrix here this W matrix here is the weight vector. It's called the weight vector, and this term here is the bias, right? So just a second. So we say that an arbitrary point is on the positive side of the hyperplane if substituting the coordinates of this point on this equation is greater than 0. Therefore, if I put a point here and the result is of this equation is greater than 0, we say that the point belongs to the class C1, or the point belongs to the if it's less than 0, the point belongs to the class C2. So that's all what there is to understand from a perceptron. Perceptron is just an algorithm that finds this hyperplane separating 2 classes, and it does that by iteratively stepping through the patterns of each of these 2 classes. It starts with an arbitrary weight vector and bias, and the task is then given a pattern vector from a population of vectors, which are this is your data. Find a set of weights such that you are able to decide whether this pattern vector, whether this data item belongs to the class C1 or belongs to the class C2. And the perceptron algorithm is very simple. I'll have to turn off my email thing. Just a second. Let me turn off my email. Otherwise, it will keep bothering us. All right. So you have to do this. So the algorithm is very simple. We have to assume certain learning rate, that's alpha, it's a correction increment or learning rate, and we have to initiate the algorithm with a weight vector with arbitrary values. So we set what we want to learn is exactly this weight vector and this bias term. But we have to start, it's an iterative process, so we have to start with an arbitrary values for these vectors and for the constant, for the bias constant. Therefore, for a number of for the examples that you have for each training examples, we set the training examples should be we're doing supervised learning. So the training examples, I know which examples belong to the class C1 and I know which examples belong to the class C2. Then I run the examples with a simple perceptron here. And I check whether for an example that should be greater than 0, if the perceptor answers greater than 0. If it answers the other way around, if the example belongs to class C1, meaning that if the example is applied to this equation is greater than 0, but the equation says it's less than 0, then I should correct the parameters of this equation, and that's basically what the perceptron algorithm does. So let's assume that that we have one example, which this xk, this is a feature vector that we know as a supervised learning, we know that it belongs to the class C1. But then if it belongs to C1, it should be greater than 0. But then when I apply the equation is less than 0. So what I do is that I correct the weight value. So for the next iteration, the weight value for the next iteration would be the old weight value plus the learning rate times this observation. And the same thing for the bias term. So the new bias term in the next iteration will be the old bias term. That's the next iteration, k plus 1. K is the previous iteration plus the increment. Why am I summing here? Because I applied my data points to this equation. It was less than 0, so I should increment something. If it was the other way around, let's assume then, as I get a second example. This is not equal to this one. This is one example that belongs to the class C2. Therefore, it should be located on the other side of this decision boundary, should be here. Whereas substituting the values of this example, the second example, this equation should give a value that's less than 0. Let's do that. Then this should give a value of less than 0. And substituting by that, it gave you a value that's greater than 0. So your perceptron is still not learning correctly. So I correct the learning weights, the weight pattern. Then I iteratively this value should be negative. Then I subtract a portion. I get the old weight and subtract a small portion of it. That is the observation times your learning rate. Otherwise, if your perceptron replied with the predicted value, then I don't do anything. I don't update the weights. I just keep the same old weights. So that's in a nutshell. That's what the perceptron does. So it goes through your example base. In this case, it got it wrong. So xk, your example is on the positive side, but it predicted negative. Then it sums stuff on the parameters. It updates the parameters by summing stuff. It got it wrong on the other side. So your example should give you a negative value, but it predicted as positive. So I should subtract something from the parameters. And this predicted right. Just keep the parameters. Okay, so the perceptron algorithm, the notation can be simplified, and that's what you're going to see in the literature of neural networks in general. This can be simplified by appending 1 at the end of every pattern vector and including the bias in the weight vector. In this sense, I don't have an equation like this anymore, because then what I did was I got this bias term and included in the matrix, in the matrix of these weight terms, and I end up having this very simple decision problem here, which basically a matrix transformation. And the algorithm is the same. So for each example, it tests each example, supervised example, that I know which class the example is. I test if your perceptron predicted the class correctly. If it did, then you do nothing. If it predicted wrong, you should fix the parameters. You should iterate on the parameters. That's a schematic diagram of the perceptron. Well, what this machine does, this very simple computational machine does, is it does the sum of products of an input pattern. What is the sum of products? That's this, right? It's the sum of product of the input parts, right? That's the sum of products of the input part of every input. So if I have an n-dimensional space, I'll have n the sum is of their n, using the weights and bias found during training. And the training is just these minor modifications on the parameters, iteratively modifying and updating the parameters. The output is a scalar value that's then passed through an activation function. That's the for the perceptron, the activation function is a hard decision boundary. So it will be +1 if it belongs to 1 to C1, or -1 if it belongs to the class C2. Right? So for the perceptron, the activation function is a threshold function. If the value is greater than a certain value, in the example that we've seen, greater than 0, then it's gonna your example will belong to the class C1. If it's less than 0, then your example will belong to the class C2. A numerical example, just to keep the ideas clear. Let's see, assume that we have two pattern vectors. These are two examples, right? Two examples. First example is a point in the three-dimensional space, having a point at the position 3, 3, 1. And let's assume that this point belongs to the class C1. And then another example that's 1, 1, 1 that belongs to the class C2. Let's assume a learning rate of 1. And the initial parameter, the initial weight vector, will be just random values we picked up, 0, 0, 0, just to make the calculation simpler. Usually these are actually random values. So for the first example, we know that it's as a supervised learning problem. I know that this example belongs to the class C1. And this is the initialization of the weight vector. Then we do the inner product. The inner product is that's what the perceptron is calculating, and that gives a value 0. So, but that's a wrong prediction. That's a wrong prediction. The perception just predicted that this example is on the boundary line and not belonging to the class C1. So I should correct the parameters. I should correct the weight values by correcting just by applying these corrections here. Just summing some stuff as we discussed before. And in the simplest perception, what I'm summing here is just the example. I'm kind of adding the example to your as a weight, as a portion of the weight vector. For the second example, that's 1, 1, 1. That should belong to C2. So the output of the if it belongs to C2, the inner product should be 0. If we calculate the inner product, it's 7. It's not negative. It's not negative. So what I do, I should apply the correction. And that is when I go through all of the training as the examples as I did now. So it was a very, very small training set. I had just 2 examples. I went through the perceptron once. This is one training epoch. What do I do now? I still didn't get the right prediction with one epoch. So what should I do? Go for a second epoch. I'm running the perceptron again with the same training examples. So if I input the first training example and do the inner product for the first training example in the second epoch, then I'll get a positive value. That's the right prediction. It's predicting that the example is on the class C1. So I don't need to update my weight vector. The weight vector will be the same at this iteration as it was before. It was calculated previously. It was calculated here, right? Here. That is 2, 2, 0. And then I use the second example that should be in the class C2. So the result of the inner product should be negative. But the product, calculating the product is positive. So it didn't converge yet. So what I'm going to do is apply the correction again, get a new set of weights. That's the end of the second epoch. If I run it once again, then the whole prediction is correct. It's going to predict example 1 as being part of the class C1, and it's going to predict example 2 as part of the class C2. And what the parameters that I got was these, that I got at the end, gave me this decision boundary here, which is this straight line, is the equation of this straight line. So now I use two examples to find what? To find the coefficients of this line and the y-intercept, which we call a bias, so that now I can predict any number of examples. As I said in the last 2 weeks, be very careful with it. I use 2 points in the training data. These are 2 points in the training data set. And obviously, I got 100% of accuracy for that. But that's why I have to now test the stuff that I've learned, test the function that I learned using the perceptron with the test set. That will give me the correct accuracy, precision, and recall. That will give me the correct behavior of the function that I just learned. And that's basically how the perceptron works. This is an example, so it keeps trying all of the training samples and adjusting this line. And this line is the decision boundary. Again, so it's going to get an initial random values for the parameters of this line. It goes iterating for every point in the data set, adjusting the parameters with small increments, in small decrements. I add a small portion. I add or I subtract a small portion of the parameters until I find the right decision boundary. Okay, is that clear? There are two people in the room today. Any question now? Because if you understood that, if you understood the simple perception, you understood a neural network. Yeah, there is a question.
Yeah, I would like to know, so how much data I need to train the neural network, and how much data I need to test the neural network.
Right, that's an excellent question. And there is no good answer for it. That depends on the complexity of your problem. I'm not sure if everybody heard that, because so Ziwen is asking how much data do we need to train a neural network model. That depends on the complexity of the data. So, and it depends on the decision boundary. If for a decision boundary that's linear like this, and for decision classes, for data sets, or for a decision problem that has a good kind of concentration on one side and the other side, so there are many nonlinear decisions that I should do here in the middle, you don't need a lot of data points and hundreds of data points. But if you have a more complex problem, we're going to see nonlinear problems. So, for instance, if you have let me get another point. If you have something like that with points here that are red, spread out, that instead of a straight line, you'd have to find some sort of nonlinear function. That you're going to need thousands of examples. But for this kind of example, I just gave you the perceptron won't solve your problem. So up to now we understood a perceptron. A perceptron, it can only be used for linear decisions, but a neural network can be used to solve these problems that you are interested now. Okay, so that depends on the complexity of the problem. That depends on the nature of your data set. Any more questions at this point? So as I said, in practice, a perceptron can only learn linearly separable classes. But linearly separable classes are rare. And this problem took the perceptron almost to total oblivion in the 80s and 90s because it couldn't learn a simple function such as an exclusive OR function. That's a nonlinear function, right? An exclusive OR that's only true if the input is 0 or 1. And it should be false if the two inputs are equal. So a decision boundary for a decision problem, an exclusive OR precision boundary would be this kind of quadratic function here. So a perceptron is incapable of finding these quadratic expressions. There were a number of attempts to solve that, and in the end, the multiply connected neural network solved this problem that we're going to see today in about 30 minutes. And it solves that by doing two things, not by assuming single perceptrons, as we did here, right? We just understood one perceptron. But by putting this kind of computational engines, a slight modified version of the perceptron that we call an artificial neuron, and making it into a network of neurons. That was one thing that neural networks do to solve to solve a nonlinear decision problem. And another thing that neural networks use is this algorithm, this least mean square error algorithm for calculating the error. So what this least mean square error algorithm is based on minimizing the error between the actual and desired response at any training example. So what we want to find is a vector, a weight vector W that minimizes the mean squared error between the actual value for the class and the desired responses and the responses of the perceptron. That's basically the error, right? That's basically the error. That's one thing that the simple perceptron wasn't doing. It was just saying, oh, there was an error, modify it with the by subtracting or adding a portion of your example where the thing went wrong. It wasn't a portion of the error. So you see the difference. The difference is subtle, but it's important. So what do we gain by assuming the mean squared error? We gain an analytical function. Whereas before we just said, oh, it went wrong, so add the example to the weights of the perception, summing the example summed by some sort of rate, learning rate, which is the alpha. Now, what we're going to do is that we have an expression for the error. We use gradient descent because what we want to get, we want to minimize this error. And in order to minimize this error, minimize this error with respect to what? With respect to the weight. We want to find the weight vector that has that leads this to the minimum value of this expression. So we get the minimum value by getting the partial derivatives of the error with respect to the weights and equal to 0. That's the gradient descent algorithm for you. And with this, assuming an analytical expression for the error in gradient descent, what gradient descent does is instead of adding or subtracting the example, I add or subtract a portion of the error on the update equations of the weights. And that's it. So basically, if I thought I turned that off. Sorry, people. a portion, if the gradient is greater than 0, a portion of this quantity is subtracted from the weight vector to create a new updated value for the weight. If the opposite happens, if the gradient is less than 0, then instead of subtracting the portion of the gradient, I add a portion of the gradient. If the gradient is 0, what does it mean? It means that I got to a minimum value of the gradient, right? So the weight is unchanged. We have arrived at a minimum. That's the least mean square error algorithm that is used in the neural network. And because this function of the least mean square error is given analytically, then it's differentiable, and I have an expression for it. And the equation for the gradient descent becomes this. So that's the update equation for the weights in the neural network. And the algorithm converges to a solution that minimizes the mean square error of the patterns of training sets. There's just there's always a caveat on these algorithms. There's always some issue that we have to pay attention to, which is with respect to the learning rate alpha. That's the parameter. That's one of the first parameters that you have to take into account. And this parameters appears in most of the machine learning algorithms that are actually of use today. So if the learning rate is too small, you are going to navigate on this function. This is the error function with respect to weight. You're going to navigate very slowly, so your algorithm will take forever to converge. If the learning rate is too high, is too large, then it's going to oscillate too rapidly, and it's not going to converge. Now, you may ask me, what would be the best learning rate? Nobody knows. That also depends on the complexity of your problem. It depends on your training examples. And that to set it up properly is a trial and error. Okay, so any questions about these the least mean square error algorithm? So what the mean square algorithm does is it substituted the update of the weight values for your perceptron by using an analytic expression that is extracted from the partial derivative of the least mean square error with respect to the weights. That's a quite smart idea, and that's the same idea that we use to derive the equations for the convolutional neural network that hopefully you're going to see today. Now we got to the multi-layer feed-forward neural networks. So basically, we're talking now about networks of these interconnected perceptron-like computing elements that we call artificial neurons. It's formed by layers of computing units, layers of these artificial neurons. The output of one unit affects the behavior of all units following it. The difference with respect to the perceptron is that in a perceptron, the activation function is a hard threshold. So it's either 1 or 0. Remember that. That's it. Either 1 or -1. So it's a hard threshold here. The problem with that is that a small variation. So if one class is -1 but has -1 due to some truncation error or due to some floating point approximations, it varied a little bit towards the right here, it will just jump to be on the other class. So it's not a very good approximator. It's not a very good function to deal with as a decision for things that involve noise, sensor noise. So first difference with respect to between perceptron and neuron, artificial neuron, is that a neuron has a smooth activation function. But the computation is the same. The computation is this sum of elements here. And that's what sum of products, right? Except for more complex notation and the use of a smooth activation function, a neuron performs the same operations as a perceptron. A neuron perceives the sum of products. What a neuron is trying to do is to approximate a linear decision boundary. The same way the perceptron was trying to approximate a linear a linear decision boundary. Then you may ask me, so how does it learn non-linear things? That's because I have a network of linear decision boundaries. And I may use a portion of, or may use one neuron that learned one decision boundary to one portion of the space and another neuron to define a decision boundary of another portion of your example space. So basically what a neural network is a composition of linear boundaries. And I'm gonna learn each one of these little linear boundaries. So the output of a neuron is denoted by A. This is the output of a neuron, and it's obtained by passing this value, that's Z, through the activation function, which has the same function as the perceptron. It is a little decision boundary, but it's a little decision boundary of a small thing that's distributed over a number of these computing units. And the input of a neuron, as this thing we're talking about, a network of these computing units, the inputs to a neuron are activation values from neurons in the previous layers. So this one was the activation value of another neuron. This one is the activation value of another neuron. This one is the activation value from another neuron in a network of neurons. What we have to learn here are these weights, and the bias term as well. But we have to learn these weights not only for one single unit, but for a network of them. So each one of these elements is one neuron in a network, and the input to this neuron will be the outputs of previous neurons interconnected, and the output of this neuron will be another neuron, unless on the last layer, which is the output layer. Well, the output layer is going to give you the decision. So the output is the output to the user, whatever the user is. And the input layer is also not a neuron. The input layer is your feature vector. So in a nutshell, what the network is doing is what the neural network is doing is distributing these perceptron-like things, which are neurons, which are learning tiny decision boundaries for distinct portions of the data set, and the composition of those gives you a nonlinear decision boundary. Let's go back. There's still a couple of things. Is that clear in a general sense what a neural network is? So there are a few concepts that we have to understand. So this activation function here, it can have many forms. It can have many forms. Sigmoid form. That's a use of a very common activation function. Hyperbolic tangent, or most modern and currently the most used activation function in convolutional neural networks is the rectilinear linear unit, or the ReLU activation function. Why this is the most used function? A simple reason: the decision boundary, the function anything that is greater than 0 will have a positive value. These are the neurons, right? The answers from the results of this calculation here. So the result of this calculation is going to pass through this activation function, and A will be the result that's output by this unit. So here, if the result is positive, then it's going to have a positive value. If the result is negative, it's going to answer 0. Why this is important? Because in a network like this, if you have too many negative values, then you have the influence of each neuron will be very small. And that's a known problem in neural networks that's been solved with the ReLU activation function. When the gradient, when you go, we are going to understand back propagation, is that once you go down and the network is very deep, if you have too many negative values for the activation functions, then the value of your gradient would just disappear. Would be too small to be taken into account. Right. So, and then we should interconnect neurons to form a fully connected neural network that's composed by layers. A layer in a network is a set of nodes called neurons in a column of the network. All the nodes are artificial neurons, except the input layer, whose nodes are components of the input pattern vector. Each layer in the network can have a different number of nodes, but each node has a single output. And the output of every node is connected to the inputs of all nodes in the next layer to form a fully connected network. The values of the first layers are the inputs. The values of the last layer are the outputs. All the other nodes, all the other layers are called hidden layers. And the neurons in these hidden layers are called hidden neurons. We call a neural network with single layers, with a single layer, a shallow neural network. And guess what? A network with multiple hidden layers are called a deep neural network. There is no secret in deep learning. Deep learning is just a deep neural network. So why is it so famous now? That's because we solved this problem with the gradient disappearing through the network. What solved it was the adoption of the ReLU activation function. Questions so far? Okay, if there's no questions, then the notation is the same as the perceptron. Perceptron, we have weights, biases, and activation functions. In this set of weights, biases, and activation functions completely define a neural network. The weight now, it has two indices, the I and J, that basically it's associating the output of a neuron J to the input of a neuron I. So I is the neuron that receives the signal, J is the neuron that sends the signal. BI is the bias value associated with the ith neuron in a given layer of the network, and we use L to denote a layer of the network. The total number of neurons in layer L is denoted by N subscript L, and the weights related to the layer L, we use this notation here. There are other notations as well, such as having L a superscript, but that's the notation that the book uses. That's the bias value for the EF neuron at the layer L, and that's the activation value of neuron K at the layer L. The task of a neural network is to determine the class membership of unknown input patterns. The task of a neural network is the same task as the perceptron, is to give an example to find whether this example belongs to a class A, B, C, D, E, or to whatever class. It's a classification. So it's the basic task of a neural network. One way to do this is to assigning a class label to each output neuron, So each output neuron will be assigned, will be representing a class label. Thus, a neural network with NL outputs can classify an unknown pattern into one of NL classes. And given that, so if I have a number of output neurons, let's say these are all the output neurons here, representing classes, and they are all going to be fired all together, right? So they're all going to have a value, an output value. Let's say x1, x2, and so on. So which class am I going to assign? I'm going to assign the class with the output that has the largest activation value. And that's it. That's all the work of a neural network. So now there are two things that we have to understand. One thing is how the classification works, how the networks operate. That's what we call a forward pass. So given a feature vector, given an input, how these neurons process this information and give you an output. We need to understand a forward pass first in order to understand the learning procedure. And the learning procedure is what happens in a back propagation. In the same sense as we've done with the perceptron, once we have this a basic neural network architecture, a basic model of a neural network, I have to assign the values for the weights and bias terms. That's the initialization of the network. Then what I do for every example, again, we're talking about supervised learning. For every example, I'm going to see whether the example agrees with the class given for this example. We're talking about training examples. Then if it's not, if it doesn't agree, if the network decision is wrong, puts this example in the wrong class, then I'm going to use gradient descent, which is the algorithm that we've learned not in a few slides ago, right? That's this algorithm, right? The least mean square error algorithm. So the neural network is going to get the error in the class classification and back propagates it. And during this back propagation, the network is going to be iteratively changing the weights associated, associated to the values, to each neuron. In a nutshell, that's all there is to this. Okay, so let's see then a forward pass. So that's going to map the input layers, values of x, to output layer, which are the classes. Values of the output layers are used to determine the class of the input vector. So here the network parameters, weights, and biases are known. And if it's a first pass, it's going to be randomly chosen. And this is not the learning process yet. The learning process occurs in a back propagation that we shall see further. So let's see the equations for the forward pass. The outputs of layer 1 are the components of the input vectors. As I said, that's your pattern vector, the pattern that you want to classify. Then a computation performed by neuron I in layer L is the sum of products given of the value of the weight and the bias. The quantity ZL is called the net or total input to neuron I in layer L, and sometimes denoted by net I. Right? And the output is also called activation value of neuron I in layer L, is given by this value, this calculated value after passing through an activation function, where H is an activation function, as we've seen before. At the output node, at the last layer, that's layer capital L, the output will be the activation of the last neuron. The last neuron that will give you a value for the classifying this example. We're using a simple numerical example, let's assume that I have as input this vector here, this feature vector is 301, and two classes, class C1 here, class C2 here. We have this X1 then is the first input neuron, second input neuron, third input neuron. That's gonna go as values to input in this first hidden layer. There's just one hidden layer in this neural network. These are values of the weights, and this is the values for the bias associated to each one of these neurons. So the calculation is very simple. In the first neuron here, the calculation will be this value 3 times this weight, 3 times .1, plus this value here 0 times .2, plus the value 1, that's this value here, represented by this this node here, times 0.6. That is the sum of that. This gives you the value 1.3. Assuming a sigmoid activation function, the output of this neuron will be this value, 0.7858, this value, right? The same thing for this other neuron here. It's going to get this value times this weight, this value times this weight, this value times this weight, and do the sum of it all, and add it with the bias, will give you this value. The same thing happens with the neurons on the next layer. We'll get this value, that's the output of this neuron after processing the input. We'll multiply by 0.2, that's the weight associated to this value, and we'll get this value for this neuron. We'll get this value, that's the output of this neuron, times this weight. This will give you this value. The same thing for this other neuron. So to which class this example belongs? It belongs to the class with the highest value. It belongs to this class here, not to this class. So this example will be classified as C1. That's very simple. That's very simple, and that's all there is. And written as sums, that's the best way for us to understand what the neural network is how the neural network works. But if we implement this as the sum of products, it's going to take a long time. As some students observed, we have a bunch of double loops that we have to run through a number of items. A better way of implementing it is by assuming another formulating the neural network as matrix operations, whereas the weight value will be the weights will be put in a weight matrix. These are the weights associated to every neuron, and the activation function is a column vector of dimension. It has to be a dimension that agrees with the weight value, containing the outputs of the layer L-1, and BL is a column vector of dimension in L times 1, also agreeing with this with the calculations that we're doing. Therefore, we don't need to do all of that sum that we've done before. This is the same example, but now expressed as matrices, and the bias as matrices. All we do is a matrix manipulation. And this is very simple. It can be implemented in MATLAB or NumPy very easily. Just 3 steps. Step 1, get the input terms. Step 2, feed forward. You just compute a matrix multiplication. Two multiplications of matrices. And then we get the activation function as output. The performance can be improved by using GPUs. In fact, a fully multiply connected neural network can work on non-GPUs, but a deep neural network will take forever to run. And especially a convolutional neural network you'll never be able to run a convolutional neural network if you don't have a GPU accelerator. Is that clear for the forward? For a forward pass, did you understand that? Because now we're going to see the back propagation. And if you didn't understand the forward pass, that back propagation will be a little bit more difficult to grasp. Any questions? No? Okay, so let's move on then. So back propagation is used in training. We don't use back propagation for the prediction or for the classification process, but for training. We use the data set to estimate weights and biases, which are all the parameters of the neural network. During training, we know the desired output. Again, we are doing supervised learning. And backpropagation is used, as I said before, to propagate the error in the output for an untrained network inside of the hidden layers of the network. We're going to use as a tool of choice for finding the value of weights and biases in a multi-layer network with many hidden layers. So in a nutshell, training by backpropagation is you input the pattern vectors, you do a forward pass, as we've seen before, through the neural networks to classify the patterns in the training set and to determine the classification error. And then we go backwards, we do a backward pass, that's called backpropagation, that feeds the output error back through the network to compute the changes required to update the parameters. And updating the weights and biases in the network is the same thing that we've done for the least mean square error algorithm. You use gradient descent. Given a set of training patterns and a multi-layer feed-forward neural network, we want to find parameters that minimize the error. And the error is also known as cost or objective function. In this case, we use the least mean square error. Means square error, not mean square. So we use the least mean square error, but we can use other error measures. As we've seen in the last practical, we used another objective function, which was the entropy, right? And there are hundreds of objective functions, but the most basic one is the least mean square error. So given the classification performance, the error is the average of the differences between the desired and actual responses, as we've seen today. The activation values of neuron J in the output layer is this value, AJL. L is the last layer, the out layer. And the mean square error is this value, right? The output, pay attention, that's what differs now a neural network with a perceptron. The output error with respect to a single example is the sum of errors of our output neurons. Is that right? Is that understood? So if you have many output neurons here, right? In this neural network, many output neurons. Each one of them will have an error, a least mean square error. So the error for one example will be the sum of this error. The error for the network will be the sum of errors for all the examples in my training set. So the total network output error over all training patterns is defined as the sum of errors of the individual patterns. So the key objective then is to find a way to adjust all weights using training patterns. To do this, we need to know how the error changes with respect to weights in the network. The weights in the network are contained in the net inputs to each node, right? The weights is in that expression. Where is the little neuron example? Right, the weights here is inside the Z. Z is the value that this neuron calculates for all of these inputs. So if I want to minimize the error, I want to get the partial derivative of the error with respect to the Z value. That's what it's doing here. In the output layer, right? Because I can only see the error in the output layer. Now I have to propagate that to the input layers, and this is done by using the chain rule. The book explains pretty well these derivations. I'm not going to get into details now because I have a lot of other things to do. But basically, it's chain rule over this expression. That's the partial derivative of the error with respect to the net output of this net input of each node. This gives you this expression here, and all the quantities are observed or computing. This is the activation functions applied to the neurons to the values at the last layer of neurons, and at the same here. So this equation tells us how so the error changes with respect to a change in the net input to any neuron in the network. And now what we want to get is the change with respect to one layer to the next layer, because we want to propagate this error layer by layer. What we do to get that, we get this expression here and use chain rule again. Use chain rule on the error with respect to every layer. And just do the chain rule from the current layer to the previous layer, or in the sense to the layer L plus 1 with respect to the layer L. And we end up with this expression here that relates the error of the layer with respect to the previous layer. Now we know how to start with an error on the output, which we can compute on the output on the big L, and obtain how the error changes as a function to the net input to every node in the network. Now we want to get to obtain how the error changes with respect to the weights and bias terms. These are done by applying chain rule again. We are going to apply chain rule in terms of the weights, and we end up with this expression here, and with this expression for the bias term. Now we have the rate of change of the error with respect to the weights, that's this expression, and bias, that's this expression. We just need to understand now how these expressions can be used to update the neural network parameters. And that's very simple. So I just substitute in the appropriate what? That's the gradient descent. That's the expression that we've seen from the perceptron since the 60s. We know that. But now we do it for every layer with a little bit of calculus, and we get to a very neat expression here. Same thing for the bias terms. So the A's, which are the outputs of each neuron, is computed by a forward pass. And these deltas, which are the errors, are obtained by back propagation. Exactly by applying these equations here. And there is also a matrix formulation that you can look at the book. I'm not going to show you that. And if you understood the maths, the algorithm for a neural network is very simple. You have your input patterns, then you do a forward pass. In matrix formulation is just a bunch of matrix multiplications, matrix operations, not only multiplications, but operations. Then we do a back propagation. all of this that I've done here, as well described in the book, has a matrix representation as well. Then the backpropagation is also a matrix, a bunch of matrix operations. And the update weights and biases is another bunch of matrix operations. It is that simple. I've implemented it many times before in my life as a matrix in Octave. I've implemented a couple of times in Octave. It's very simple to implement it. Very simple. It's just following this recipe. And you get amazing results, such as the solution to the exclusive OR problem. The book does it. It has a historical interest. If you are interested in the history of neural network and history of AI, or in particular the history of neural networks, have a look at the book about how the multiply connected feed-forward neural network solves the exclusive OR problem. And basically, you can solve it. You can't solve it with a single perceptron. You can't solve it with a single neuron, but we can solve it with one hidden layer. And you have to have these connections. Now you may ask me, how do I know how to connect this? A fully connected is dense, right? Every neuron in a layer is connected to every previous neuron in the previous layers, right? There's no secret. There are other architectures of neural networks, as you may guess, and each one, the literature tells you about it. That's an introductory lecture on neural networks. But with that, with the fully connected, you don't need to be worried about how these neurons are connected. They're densely connected. Remember in the previous practical that I said, well, this is a dense layer. That's what it means. That's what it means. That's a dense layer. It means that every neuron is connected to every other neuron in the previous layer. Now, we can use that to classify, well, basically to classify any sorts of data. In particular, the book gives this example, which is the classification of multispectral image data. I have to remind you that we are still talking about a classical multiply connected neural network where the inputs are feature vectors. So I should get all of this data, spectral bands, and turn it into feature vectors. And one way of doing that is just getting every pixel, assuming that they are normalized images, by getting every pixel and feeding it in one vector. This will be one input point for the neural network. So there's going to be, if I have 212 by 212 pixels, then I'll have to have a 212 by 212 inputs to the neural network. You can simplify that and you can generate a longer feature vector, not only single, like crossing all of those. There are ways many ways of representing it. And the classification task is to classify water, urban, and vegetation classes. And that's the recognition rate with the network architectures with 4 input layers, 4 inputs. Each one will be one. Each input will be one vector representing one spectral band, the way they implemented it. So the first feature vector will be one spectral band, the second will be the second, third, and fourth, represented as vectors. So all the inputs will be 4, because I have 4 spectral bands. And this is the number of hidden layers. And the outputs will always be 3, because I want to classify in between water, urban, and vegetation. So I have 3 outputs. With 2 hidden layers, then I got almost 96% of recognition rate. 3 hidden layers, 96.2. 4 hidden layers, not much of a change. 5 hidden layers, more or less the same thing. So basically, if you have just 1 hidden layers, I've read it wrong. So this is 1 layer with 2 neurons. This is one layer with 3 neurons. This is one layer with 4 neurons. So you see that the change from 2 neurons to 3 neurons wasn't great. This change wasn't great. So with one layer, I could keep adding neurons to one layer, but the recognition rate wouldn't be better. But let's try to add more hidden layers. So this has 2 hidden layers, one with 2 neurons, the other with 2 neurons. The result was terrible. Let's then keep adding layers, 4 layers and 3 layers, slightly better. 4 layers and 4 layers, slightly better. 10 layers, 10 layers and 10 layers. So what does it mean? I just had one hidden layer with 2 neurons, gave you a value that's very good. And once I started adding more layers, the value was the recognition rate degraded. That's what I said from the beginning of this topic. You know, you have this bunch of computational units, and they are very good for finding linear decision boundaries. But for nonlinear decision boundaries, then you have to find some sort of interplay between all of these little linear units, and depending on the complexity of your example, and depending of your problem, and depending the kind of data, it's difficult to predict. So what the book did here is correct, and that's how we work with the neural network. We try it out. We try different architectures and just see which one fits better the data. In this case, this architecture fit much better the data than a more complex architecture. Just live with that. This is given the for this neural network. This is the weight value, the weight matrix that the network learned in the bias matrix for the first layer, which is this one, and this is related to this layer here. Okay, the weight matrix and the bias matrix. Now that's interesting. So that's for the same recognition problem, the recognition performance of the training set as a function of training epochs. Remember that one training epoch, you go through all the data once, and this guy, we've run the training epochs 1,000 times. We got a recognition rate of 95%. We've run the 50,000 times. 50,000 training epochs. We've run the whole training set 50,000 times. We got a recognition rate of 97%. And that sort of got to a standpoint, right? It converged to a point, because for 600,000, 700, 70,000, 60,000, 70,000, 80,000, the recognition rate wasn't improving a lot. So that's more on this problem. This is the mean squared error of the network with respect to the training epochs. So it converged really fast to a good value, 0.1 or more or less 0.8, 0.08 or 0.1 for the mean squared error. Let's play a little bit with all of this. So you can then play yourself, just for fun. This is a great site that I found today, where you can build neurons. Yeah, you can add hidden layers. You can add hidden layers and then just run. to see your neural network converging to a decision boundary. This is a non-linear decision boundary, right? So this is a quadratic function that separates the blue examples, which are the examples from one set, with respect to the orange examples, which are the examples of the second set. And I managed to break it. Let's see if I can break it again. Let's put 2 neurons in the first layer and 2 neurons on the second layer. It's taking longer, right? It's taking much longer. And I think I'm going to break it. Yeah, just broken it. It didn't find a decision boundary. Why is that? Well, the hypothesis is that this neuron learned this decision boundary here, right? This decision boundary. This other neuron learned this other decision boundary. They are linear decision boundaries. They don't learn. One single neuron do not learn nonlinear things. So in the composition of these decision boundaries, did not give the proper function, right? Did not give the proper function. Let's add neurons. Here it is. Here it is. So you see, these are still linear decision boundaries. Then this neuron managed to compose these 3 decision boundaries, the results of these 3 decision boundaries, into this decision process here. And you see that this is this neuron is receiving more weights. It learned the weights that it learned was more had a higher value than the weights this one learned. And this one kind of learned a weaker decision boundary here, right? You can see that. And the result of combining these 2 neurons here at the output was this very nice, neat decision boundary with a very good, very efficient, with training loss 0 and test loss 0, almost perfect. Nice, isn't it? Okay. Then next step is to do go through the convolutional neural networks. Let's give it a 3-minute break, and then I won't have too much to say about convolutional neural networks because you've learned everything about neural networks today. And I will stop the recording now and restart in 3 minutes. If you do you have any questions now? There are 2 people in the room. Questions? Okay, so what you can do now is play with that neural network. I'll keep that. That will be great fun. That will be great fun. Let's play on with that for 3 minutes. You're gonna enjoy that.